Based on the number of relations in the Cartesian product, we have different types of relation. When we say it is the null relation, so there is no ordered pair which have the relation R between A cross A. So clearly null relation is an empty set. Reflexive relation is nothing but, suppose we have defined a relation R on an empty set A, then if A contains an element A, then A comma A must be in set R. Hello everyone, a warm welcome to one and all. This is your Shruti ma'am lecturing in Vidhyaashram, the Temple of Excellence, Mysuru. Here in this session, we are going to study about the types of relation. So we have learned the relation as a subset of a Cartesian product. So whenever A cross P is defined, it is the set of all ordered pairs between the two sets A and B, whereas the relation is a set of ordered pairs which contains a relation between the elements of A and B. So obviously relation is a subset of Cartesian product A cross B. So based on the number of relations in the Cartesian product, we have different types of relation. So the first one is the identity relation. What do you mean by the identity relation? Let A be non-empty set. The relation IA defined by A comma A for all A belongs to A is called the identity relation on A. So the relation from set A to itself is nothing but the identity element. So in this relation, it contains the element of the form A comma A, where A belongs to the domain as well as, and second element A also belongs to the domain. So we have written here A belongs to the set A. So such type of relations is called as identity relation. For example, if I consider set A is equal to 1, 2, then R, which contains element 1, 1 and 2, 2 is called as identity relation on set A. The next is the null relation or void relation. So as the name itself says, when we say it is the null relation, so there is no ordered pair which have the relation R between A cross A. So clearly null relation is an empty set. Let A be a non-empty set. We know that empty is a subset of Cartesian product A cross A. We know that relations are nothing but the subsets of a Cartesian product, and we have learned from the concept of sets that every set contains empty set as in its subsets. So hence the set empty is also a relation on the Cartesian product A cross A. This relation is called as null relation on A. Now universal set. So we know that every set is subset of itself. So A cross A should be subset of A cross A itself. So when I say the universal relation, it forms a universal set. Since A cross A contains all the ordered pairs between set A to set A, we have all the ordered pairs here. So therefore, it forms as an universal set, and hence a relation between set A with respect to itself is called as universal relation. Next, we have a reflexive relation. So, reflexive relation is nothing but, suppose we have defined a relation R on an empty set A, then if A contains an element A, then A comma A must be in set R. For example, if we have A, B, C here, then R1 is a relation which contains A comma A, B comma B, and R2 is a relation which contains A comma A, B comma B, C comma C. So these are called as reflexive relation on A. So this is almost the same as your identity relation. Now, the identity relation and universal relation on a non-empty set or reflexive relation, because identity element contains an ordered pair which is of the form A comma A, and reflexive also contains a relation of the form A comma A, and hence we have here set R1, R2 as a reflexive relation, and hence we can conclude the identity relation as well as the universal relation forms reflexive relations. Next, we have symmetric relation. Suppose we define a relation R on the set A. Assume that we have an element 2, 3 in the relation. Then there should exist 2, 3 as 3, 2 in the relation. For example, if we have A, B in set R, that means inside the relation, then there should exist B, A in the relation. Then only we call it as a symmetric relation. For example, consider the set here 1, 2, 3, 4, 5. Let R1 be the relation 2, 3, 3, 2, 3, 4, 4, 3. Now, consider the element 2, 3. So, this is belongs to R. Do we have 3, 2? Yes. Now, consider the element 3, 4. Does we have 4, 3? Yes. So, for all the elements in the form of A, B, we have B, A in the relation. So, therefore, R1 is called as symmetric relation. Now, let's take one more set here. 1, 5, then there should exist 5, 1. Let's take 2, 5 from the set A, then there should exist 5, 2 in the symmetric relation. Now, let me take one more relation, R3. So, let me consider R3 as 1, 1, 2, 3, 4, 3. Now, consider this relation R3 which is defined on the set A. So, we have an element 2, 3 but there does not exist an element 3, 2 and also 4, 3 exists but there is no 3, 4. Is it a symmetric relation? No, this is not a symmetric relation. So, for every pair of A, B, there should exist B, A in the relation. Then only we say it as a symmetric relation. Now again here universal set contains all the elements in the form of A, B as well as B, A and hence universal set is also an example for symmetric relation. Next is transitive relation. A relation R on a non-empty set A is called as transitive relation if there exist ordered pairs A, B, B, C in the relation R, then there should exist A, C belongs to R. For example, let me define in the set A 1, 2. Now, I will define the relation R here. So, 1, 1, 2, 2, 1, 2, 2, 1. Now, according to the condition, we should choose two ordered pair in such a way that 1, 2 is there. Then, let me take 2, 1. Then, A, C should be there. So, if I say 1, 2 is in R, and 2, 1 is in R. Does 1, 1 belongs to R? Yes. 1, 1 belongs to R here. Therefore, this is a transitive relation. Now, let me consider in the reverse process. Let me consider 2, 1 and 1, 2. So, 2, 1 is in R. 1, 2 is in R. Does 2, 2 is in R? Yes. We also have 2, 2 in R. So, therefore, this is an example for a transitive relation. But if I take this R as 1, 2 and 2, 1. Now we have 1, 2 in R, 2, 1 in R, but we don't have 1, 1 in R. Similarly, we don't have 2, 2 in R to satisfy the transitive relation. So this is not transitive relation. This is only symmetric relation because for every 1, 2, we have 2, 1. So, for every A, B, we have B, A. So, therefore, this is an example for symmetric relation but not transitive relation. Now, let R be a relation on the set of natural number defined by x is a factor of x. When we consider x is a factor of x, we write x, y belongs to R. So, if x is a factor of y means x divides y. And also we will consider y is a factor of z, which means y, z belongs to R. So, here x divides y and here y divides z. Obviously, if I take an example of 2 divides 4 and 4 divides 8, then obviously 2 should divide 8 because 2 divides 4, 2 also divides 8. So, clearly here also we get x divides z. So, that implies x, z belongs to R, which means x is a factor of z. So, therefore, this is clearly an example for transitive relation. Next, we have equivalence relation. So, a relation which is reflexive, which is symmetric and which is transitive. That means which satisfy all the properties of reflexive, transitive and symmetric is said to be an equivalence relation. For example, let me consider similar to. The relation similar to or we can also take the relation congruent to, or we can take a relation parallel to when it comes to the geometry. Now let me consider three triangles here. Similar means same shape, congruent means same shape and same size, and when we say parallel, when we talk about the lines. First let me explain the condition of similar to. Let me consider the triangles T1, T2, T3. So when I talk about the reflexive, so first property is reflexive. So we know that every triangle is similar to itself. So therefore it is a reflexive relation. That means we can say T1 comma T1 belongs to the set R. So what does the reflexive relation say? For instance, suppose there exists an element which belongs to the set A, then A comma A should belongs to set R. So therefore, if T1 belongs to the set of all triangles, then T1 comma T1 under the relation similar to belongs to set R. Now similarly, if I consider about the symmetric relation. If triangle T1 comma T2 belongs to R, what does it mean? T1 is similar to T2. If T1 is similar to T2, obviously T2 is also similar to T1. That means here we get T2 comma T1 belongs to R. So therefore, this is an example for symmetric relation. Now let's talk about the transitive property. So when I talk about the transitive property, by looking at the diagram, we can say if T1 is similar to T2, T2 is similar to T3, then obviously T1 and T3 are similar to each other. So which satisfy the condition of transitive. So therefore, this condition of similar to is an example for equivalence relation. Now if I remove the word similar and put back the congruent here, so we know that every triangle is congruent to itself. So therefore we exist an ordered pair of the form A comma A, and hence it is reflexive. If two triangles, for instance, T1 is congruent to T2, then T2 is also congruent to T1. So obviously it is a symmetric relation. Now considering the three congruency here, T1 congruent to T2, T2 congruent to T3 implies T1 congruent to T3. So obviously the relation congruent to is also an equivalence relation. Now let me consider parallel to. So we know that every line is parallel to itself. So that means it's a collinear. Every line is parallel to itself. So obviously it is an example for a reflexive relation. Now let me consider two lines L1 and L2 which are parallel to each other. So if I write L1 is parallel to L2, then it also implies L2 is parallel to L1. So it satisfies the symmetric property. So therefore this is an example for symmetric relation. Now let me consider one more line here. Let me consider this as L3. Now assume here L1 is parallel to L2 and L2 is parallel to L3. See, L2 is parallel to L3. Then obviously L1 and L3 must be parallel to each other. So again it is satisfying the transitive property. L1 parallel to L2, L2 parallel to L3, which means L1 is parallel to L3. That means all the three lines are parallel to each other. So if I consider L as the set of all lines which are parallel to each other, and if I use the relation of parallel to between the lines, then it is also an example for equivalence relation. Hence, these relations similar to, congruent to, parallel to and a geometry comes under an example as equivalence relation. Next type is antisymmetric relation. So a relation or non-empty set A is called antisymmetric relation if A comma B, B comma A belongs to R, so that A is equal to B. So here I have taken an example. Consider the relation R defined by E is less than or equal to on the set of integers. So now let me consider here X comma Y belongs to R. When I say X comma Y belongs to R, using that relation we can write X is less than or equal to Y, or y is less than or equal to x. So when I say x is less than or equal to y or y is less than or equal to x, then obviously x and y should be the same. So therefore this is an example for anti-symmetric relation. We have also studied one more definition under set. If A is subset or equal to B, it is not proper subset. So when I say proper subset, I'll just write A is a subset of B. So but here there's a difference. A is subset or equal to B, or B is subset or equal to A, then obviously A is equal to P. So this is a definition of your equal sets. So in the similar way, we can take here if we exist a relation less than or equal to 2. Or we can also take the relation greater than or equal to. So if x is greater than or equal to y, or if y is greater than or equal to x, then there also x is equal to y. So this is an example for anti-symmetric relation. Next, if A is equal to 1, 2, 3, 4, 5 and B is equal to 1, 2, 3, 4 and R is a relation from A to B defined by R is ordered pair x comma y and y is in the form of 2x plus 1. Find R. So we know that when we define a relation, the first set falls as a domain and the second is the codomain, and always the range will be in the second set. So that means x should belongs to the first set and y should belongs to the second set. It should not exceed your second set. Now the first ordered pair which I can take here, if I take the value of x as 1, then here 2 1s are 2 plus 1 3. So my first ordered pair is 1, 3 where 1 belongs to A, 3 belongs to B. Let me take 2 here. So now if I take 2 from the first set, 2 2s are 4, 4 plus 1, 5. So we have 2, 5, but this does not belongs to the relation set because 2 is in A but 5 is not in B. So therefore the only element of this relation is 1, 3. 1 acts as a domain and 3 is the range of the given relation. Next question. Give an example of a relation which is reflexive but not symmetric and not transitive. Let me take a set A here which contains the element 1, 2, 3. I need only reflexive property but not symmetric and not transitive. So to make the relation reflexive, for every element there should exist an ordered pair A, A. That means for 1, 1, 1, for 2, 2, 2, for 3, 3, 3. Now write an element which obeys the condition as not symmetric. Now let me take a pair 1, 2. If 1, 2 is there, then there should exist 2, 1 to make the relation as symmetric. But here I'll just write 1, 2 because it says it is not symmetric. Now let me take an example 2, 3. Now 1, 2, 2, 3 is in R, but 1, 3, if it is in R, then it becomes transitive, but I need it as a not transitive condition. So I'll end the relation set here. So 1, 1, 2, 2, 3, 3 satisfy the reflexive condition. 1, 2, 2, 3, we have an ordered pair, so which neither satisfies the symmetric property nor satisfies the transitive property. So this falls as an example for a reflexive relation which is not symmetric and transitive. Now next is symmetric but not reflexive and not transitive. So I can take an example of a relation which has 1, 2, 2, 1 in the set, on the set A is equal to 1, 2. See here set A contains 1 and 2. For a reflexive, it should contain 1, 1 and 2, 2, but here it is not there. So it is not reflexive. For a transitive condition, there should exist a third element. Again, it does not satisfy transitive condition, but it satisfies the symmetric property because for 1, 2, we have 2, 1. And we can also give an example of perpendicular to relation. A relation perpendicular to is an example for only symmetric relation but not reflexive and not transitive. For example, if I consider a line here, a line L1, every line is not perpendicular to itself. It is only parallel to itself. So here it does not satisfy the reflexive property. Suppose I consider a line L2 here. Clearly L1 is perpendicular to L2. L2 is also perpendicular to L1. So it satisfies the symmetric property. Let me consider L2 is perpendicular to L3. See, L2 is perpendicular to L3. So obviously L3 is also perpendicular to L2. But L1 perpendicular to L2 and L2 perpendicular to L3 does not implies L1 perpendicular to L3. When you observe here, L1 is parallel to L3. So this does not satisfy the transitive property. Next we have transitive but not reflexive and not symmetric. We can use the condition of less than or greater than as a relation. So transitive, it is less than. Suppose if I say x is less than y and y is less than z, then obviously it implies x is less than z. And similarly, if I apply greater than, x is greater than y is greater than z, then obviously x is greater than z. But when I include equal to here, it satisfies transitive and symmetric property. So the relation which is only less than, or we can say strictly less than or strictly greater than, is an example for a transitive relation but not reflexive and not symmetric. Why it is not reflexive and not symmetric? Because I cannot write x is less than x. And if I write x is less than y, then thus does not imply y less than x. Either one of the condition will satisfy, not both. So therefore, neither it is reflexive nor it is symmetric. Next question, a relation R is defined on the set of integers R x comma y. X minus y is a multiple of a non-zero integer phi. Show that R is an equivalence relation. So clearly, if x minus y is a multiple of a non-zero integer phi, means if x minus y is a multiple of phi, that means phi divides x minus phi. So let us prove the property of reflexive, transitive and symmetric one by one, so that we can prove that it is an equivalence relation. Now here, clearly x comma x belongs to R. If x comma x belongs to R means that implies phi divides x minus x, which implies phi divides 0. So it satisfies the given condition. So therefore R is reflexive. Now let us consider x comma y belongs to R. If x comma y belongs to R, then that implies phi divides x minus y. So that also implies phi divides y minus x. If phi can divide minus of y minus x, then phi can also divide y minus x. So that implies y comma x belongs to R. So for every x comma y, there exists y comma x in R. So therefore, R is symmetric. Now let us see the third property. So that is transitive. So let us consider an ordered pair x comma y belongs to R and y comma z belongs to R. Then that implies phi divides x minus y and phi divides y minus z. So let us take the sum of these two elements, then x minus y plus y minus z, which is divisible by phi. So here you can clearly see y divides x minus z. So if y divides x minus y, then x comma y belongs to R. So if phi divides x minus z, then x comma z belongs to R. So for every x comma y and y comma z, we have x comma z in R. So therefore, R is transitive. Since R is reflexive, R is symmetric and R is transitive, so this implies R is an equivalence relation. The last type of relation is the inverse relation. So what do you mean by this inverse relation? Let R be a relation from A to B. The inverse relation of R is denoted by R inverse, that is R to the power minus 1, and it is a relation from B to A. So let us take an example with the problem here. So if R inverse is equal to 2, 4, 1, 2, 3, 1, 3, 2, find R. So since it is an inverse relation, so reversible from A to B to B to A. So we have a relation R. So example, let us consider from B to A. Then I have to write a relation from A to B. That means my ordered pair changes. So therefore, R is equal to here 4, 2, 2, 1, 1, 3, 2, 3. So this is a relation R and this is its inverse relation. So in this session, we have learned the types of relation. I'll meet you in the next session. Until then, keep watching, keep learning, keep exploring. Thank you.